Welcome back to Calculus with Applications as we continue with our third week of remote learning. Before proceeding with this video, you should open the Integrating Negative Velocity Functions video capture sheet provided. You'll be asked to complete tasks in the document throughout the video. We're still in Unit 5, where we're studying the integral. In the first part of the lesson, you learned how to evaluate definite integrals for functions that may drop below the x-axis. We now turn our attention to the context of particle motion, and we will connect the velocity and position functions using the definite integral. As you explored with the applet, you noticed that the blue particle in the box moved right on the number line when velocity was positive, and left when velocity was negative. If you have not already done so, pause the video and write down on which intervals the particle moves left and right. The particle moves right whenever the graph of the velocity lies above the horizontal axis. In this case, that's between 0 and 2 seconds and 6 and 8 seconds. And the particle moves left whenever the graph of the velocity lies below the horizontal axis, namely between 2 and 6 seconds and 8 and 9 seconds. What is happening at 2 seconds, 6 seconds, and 8 seconds? Pause the video to think about this. Because velocity is 0 at each of these moments, the particle is stopped and is not moving left or right. We can also say that the particle changed direction at these times. These are important observations, but we want to push our analysis further. In fact, all of these results were discussed earlier in the course in the context of derivatives. Using what we now know about integrals, we can be more specific about the motion that is occurring. Can you see how the area of the blue shaded region on the velocity graph relate to the current position of the particle at t equals 2? When we say that the particle moves right on the interval 0 to 2, we can now report how far to the right the particle traveled during this time. It's simply the definite integral of the velocity function from 0 to 2. And the same can be said about the other intervals. Evaluating all of these integrals, we have the following. From this example, it should be clear that the definite integral is a powerful tool that allows us to extract detailed position information from the velocity function. Watch the following short clip. If someone were to say, "How far did Olivia go?" how would you answer? Pause the video to think about this question. One person might say she went nowhere since she returned to where she started. Another person might say she went 18 meters since that's how much total ground she covered. There is a sense in which both are correct and useful answers. The first answer, 0 meters, is useful if you're looking for information about Olivia's location. The second answer, 18 meters, is useful for knowing how tired Olivia is. We now define the terms displacement and distance. The displacement of a particle is its location relative to where it was when it began, reported as a negative or positive number. The displacement is simply given by the definite integral. In this example, Olivia's displacement was 0. The distance traveled by a particle is the total length of the path traveled by the particle, reported as a positive number. The distance traveled is simply the area between the velocity function and the x-axis, and is always positive. In this example, Olivia's distance traveled was 18 meters. Let's now return to our previous example with the lens of displacement and distance. The graph of the particle's velocity appears on this slide, and this time the integral values are shown on the graph. What is the displacement of the particle between 0 and 9 seconds? Pause the video to answer this. The displacement, remember, is simply the definite integral. Integrating from 0 to 9, we obtain -1. The way to interpret this is to say, after 9 seconds, the particle is 1 meter to the left of where it started. What about the distance traveled by the particle on this interval? Pause again to answer this. The distance, remember, is the total area of the regions. In this case, we form the sum of all these areas, reporting each as a positive number. And we obtain 6 meters as our answer. Notice the use of the absolute value. Let's ask 2 additional questions. When was the particle at its rightmost point? When was it at its leftmost point? Pause once more to consider this question. There are 2 possibilities for the rightmost time, t equals 2 and t equals 8 seconds. The reason these are candidates is because they represent the last time before the particle starts moving left again. If we integrate from 0 to 2, we obtain 1.5 meters. And if we integrate from 0 to 8, we obtain -0.5 meters. So at t equals 2 seconds, the particle is at its rightmost point. There are 3 possibilities for the leftmost point, t equals 0, t equals 6, and t equals 9. Integrating each of these, we obtain 0, -1.5, and -1. So at t equals 6 seconds, the particle is at its leftmost point. Notice once again how much information we can learn about the position of a particle by analyzing integrals of the velocity function. In part 1 of this lesson, we compared area and the integral. Here's one of the problems we looked at. Which of these values corresponds to displacement? Which corresponds to distance? Pause the video to answer the question. The first calculation corresponds with displacement, and the second with distance traveled. After this lesson, you should be able to describe the difference between displacement and distance and how these relate to the integral.